Hey, pre-calculus. So welcome to the boat in the river problem, part one. So it's otherwise known as the escalator problem, because as you're aware, there's a guy riding on an escalator. So our learning target today is that you will investigate real-world motion. And if you remember, the first step in George Polya's problem-solving principles was to understand the problem, right? So we did that the other day. We decided that the problem that we were being asked, that we're going to try to find out the answer to, is how long will it take that guy to go up the down escalator, right? And we've had an opportunity now to talk about in our small groups some different ideas that we could have, right? Step two in the problem solving principle, step two is to make a plan. And so there's lots of different ideas that come into this formation of a plan, right? We could think about like, so I've collected some of them from different groups and different classes. And so here's just a collection of different ideas that people have come up with as like, maybe this is our plan, right? So we can look at how long is the escalator, how long is it going to take to go up the stairs, how much time will it take to go up the stairs, how fast, we can look at speeds, how fast is the escalator going, how fast is the man walking. We could subdivide, we can look at the size of each of the stairs, the size of each of the steps on the escalator. We could try to use proportions, when at the end, that cliffhanger ending, when he was partway up the down escalator, if we knew what fraction of the way he was up, we could use a proportion to find out the amount of time it will take him to go all the way up. We could find the speed of the escalator as it is moving. We could find the time that it takes the escalator to do one full trip. There's a ton of different things we could do. There's so many different ways to approach this problem. It's awesome. I love it. There's so so many options for creativity. But we need to focus. We're going to bring it together. So maybe some of you know Mr. Matthews. He teaches physical science and physics, and I used to teach physics, but I learned a trick from him. So when we're studying motion, there are these three variables we got to keep track of: velocity and distance and time. And so there's a set of formulas that we can use to calculate. If you know any two of those, you can calculate the third, right? So velocity is distance divided by time, times distance divided by velocity, distance equals velocity times time, right? And if you're big into memorizing formulas, or just if you use them often enough, you memorize them, but not everybody can memorize them very easily. And so that's where Mr. Matthews' magical mnemonic monument of motion comes in. It's this cool triangle. So in the triangle, we've got the three letters: distance, velocity, and time. And the triangle helps you to remember what the formulas are so you can calculate things. So as an example, let's look at this yellow formula. If you need to find the velocity, you're going to cover up the v part of this triangle because it's unknown. You don't know that, right? And then what's left? What's left is that's the formula. So it says distance on top of time. That means divide by distance, divide by time, just like this yellow formula says. What if I didn't know the time? I need to calculate how long is it going to take this thing to move that far, right? Well, if I know the distance that it is moving, the velocity it is moving at, then I got the d on top of the v. This means divide, distance divide by velocity, just like that green formula. That's time. The last one, what if I don't know the distance something will go? If I know the velocity it's moving and how long it keeps going at that velocity, I got the v right next to the t. That means multiply velocity multiplied by time, just like this blue formula right here, right? So trying to focus, trying to subdivide, get some smaller parts. The ending question is how long, how much time is it going to take for the guy to go up the down escalator? But to get there, we got to focus on some smaller parts first. We can't just jump straight to the end, right? We got to go through this process. And the first part of the process is the boat, right? It is called the boat in the river. And this guy right here, he's the boat, right? So we're going to focus on the boat. And it's a metaphor. It's actually he's a man, not a boat, but it's a metaphor. He's like the boat. It's really, really deep. It's like the river. It's deep. Okay, well, so we're going to focus on the boat. The thing we want to find out about the boat is how fast can he move, right? He's walking up the stairs, he's walking down the stairs, he's walking on the escalators. The escalators going the same direction, the escalators going the opposite direction. All right, but how fast does the boat go? All right, well, to figure out how fast the boat goes, we need to know something about the boat's environment, right? So in the video, we've got some stairs and escalators, and I overly simplified with terrible drawings. It's the best I could find. Um, so we've got the staircase, we've got an escalator. Spoiler alert, I do have some more information about the stairs and the escalators that we'll be able to use. Um, but there's still some things we need to come to agreement on. We have to make some assumptions, right? And so I think you think about construction. When they built, it's an empty movie theater. When they built the movie theater, there's like this ramp, right, that goes from the ground floor up to the first floor. When they build that ramp, I think it's pretty safe to assume that everything starts at the same place. The escalator starts at the same place that the stairs do, right? They both end at the same place. It's that ramp is attached where the stairs and the escalator are built onto the ramp. It ends at the same place up here on the first floor, right? So although the shape of the staircase is different than the shape of the escalator, that's fine. We can have different shapes, but they start at the same place and they end at the same place. So our distances are the same, whether we're measuring distance on the stairs or on the escalator, right? So that's important. Okay, so like I said, I have some more information that I have not shared with you yet. So let's take a look at the escalator. Let's see if I can get this thing to open. We'll take a look at what the escalator looks like. Hmm. All right, so as we get up here to the top of the escalator, I'm going to point something out. You can see we're staring at a problem right there. I don't know if you know that this is a problem, but that is a problem. That stair is not fully extended. That's the way escalators work, right? You've got all these stairs and they're like hidden in the ground and then they magically appear and they pop up. They're flat for a while and then the steps grow, right? They get taller and they extend. At the very top of the escalator, they shrink back down and they go flat, right? And so this stair is not fully extended. The same thing happens at the bottom. The bottom of the escalator, there's some of those stairs that are not fully extended, right? They're flat. And that makes it really, really difficult for us to do any kind of measurement with the escalator, because even though I do have measurements about how long, I call the depth, but that's the length of the escalator step, and the height of the escalator steps. When we have stairs that are not fully extended, that makes things really complicated. So I mean, I can zoom in here. We can see what that measurement is. But when you got some stairs that you can't tell how far extended they are, it's going to make it a big mess for us to calculate any kind of distance with the escalator, right? Also, so that's the height. If we think about the length, some of those escalator stairs are like hidden underneath the platform. They're not like fully exposed yet. We're gonna have the same issue with both the height of the escalator steps and also the length of the escalator steps because not all of the steps are actually there fully, right? So I'm gonna back up. Okay, so we got an escalator, we got a staircase. They both have the same start and end point. Escalator is going to be tricky for us to get an accurate measurement on. So we're going to look at the staircase. All right, let's start with the easy part. Let's think about how high that staircase goes. What is like the elevation change for the entire staircase? Right, that's not very complicated. If we think about it, there's a bunch of steps. This is not an actual drawing of that staircase, but there's a bunch of steps. And usually when we have stairs, each step is the same size. So all we have to do is find out how many stairs there are and how high each one is, and we'll be able to put those all together. You probably can multiply and do it faster to find the total height. That's like a vertical distance of the staircase, right? So let's start with that. So here's what the stairs look like. We'll need to know how many stairs there are. All right, so I'm going to stop it right there because he turns around and the camera goes all wonky and you get like seasick watching it. Okay, so in that video, it was really clear. I mean, you could count the number of stairs. I gotta keep track of what we're talking about here. So you can count the number of stairs, and I got to show you how high each one of those stairs is, right? So we're gonna try to use not whole numbers. We try to round. Let's go with decimals. I know the tape measure here is going to show us fractions, but we're going to go to at least one decimal place of accuracy, and I mean two probably is better. But there's the top of the stair right there. Get a nice long look at that. All right, so that is the height of each of the stairs. We're gonna say every single one of the stairs on that whole entire staircase has the same height, and that's what it is. Okay. Well, in the video, we also saw that in the middle of the staircase, one of the stairs was longer. It was a big platform stair, right? So if we want to find how far sideways, the horizontal distance of the whole entire staircase, we know how many stairs there are. So a bunch of the stairs just are these small stairs, right? So we can put all those together. And this one at the top too. You still got to step on that one, and also this one long platform stair in the middle. We just got to add that one in there, right? So we need two length measurements, and then we can multiply by the number of stairs that there are in there. Okay, so that big platform stair, let's start with that one. It is right there. Oh my gosh, look at his feet. Yuck. All right, so you can see where the shadow line is. There's the measurement for the platform stair. There's only one of those. And the other stairs are all this size right there. It looks like it comes out at a nice round number. Even if we're trying to go to decimal places, I'm not sure that there's a decimal place to be had there. All right, so that was the length of all of the other stairs, the rank and file stairs that are all the same. All right, so we're gonna put all that together. Right, we're gonna keep track of two separate distances. Right, so here's our almost to the end. We're gonna calculate two different things. Here, we're gonna calculate a vertical and we're going to calculate a horizontal velocity. Okay, to get the vertical velocity, we're just going to take his vertical distance right there. To find velocity, we need distance divided by time. The vertical distance, that's the elevation change. What is the total height in the whole entire staircase, bottom to top? How high is that? What is that distance? Okay, we just calculated that. And then we're going to divide it by the amount of time it takes him to walk up the stairs. And we'll have to watch the other video to get that time. Okay, next, it's going to be a similar process. It's the same calculation, but with a different measurement. So to get his horizontal velocity, we're going to take his horizontal distance, right? That's the sideways length of that whole entire staircase, all the stairs together. How far sideways does he end up moving, right? So I know in real life he does not actually move horizontally and he does not actually move vertically, right? He's going diagonal up the staircase, but we're going to take this, we're going to break it apart into these two different components. We're going to keep track of these two measurements separately. So we've got a vertical calculation, a vertical measurement for the distance, and we calculate the vertical velocity, the aspect of the velocity. And we're going to do the same process for the horizontal distance. We'll use the horizontal distance to calculate the horizontal aspect of his velocity. Right. Well, both of these calculations do have the same time, right? So we're going to need to watch the original video to find out how long it takes him to go up the stairs. And then we'll be able to calculate these things, right? So here comes our favorite video, the soundtrack. Oh my gosh. Man, I was rocking out and I totally missed it. I have to back up and watch that again. Oh, hey, there it was. I saw he made a little hand gesture when he's over here at the bottom of the stairs because he's off the screen. That's handy. All right, check this out. So I'm going to use technology. All right, so we're going to go frame by frame so we can try to isolate the time that is hand. You can see his elbow right there, looking over on the left edge of the screen. We're gonna wait for his hand. Oh, here comes his hand. There's a blur. Here it comes. Blam! There it is. Look, you can even see there's stepping up on the top stair up here. You got the hand signal right there. You get the time highlighted in a different color. This is a weird thing. We're going to pretend like it's a colon, but it's not actually a colon. It should be a decimal point. So we got seconds, and over here, hundredths of seconds. All right, so there's our time. We got a time. And now we can calculate these two velocities. All right, cool.